Okay, Math 230 class. As I promised, I'm going to give you guys a video here which will finish off our section 1.2, and then we're also going to do 1.3. In order to keep these videos a little bit shorter, I'm going to do two separate videos. I'll finish off 1.2 in one video, and then I'm going to do 1.3 in another video. 1.3 is a little bit longer because it has a bunch of calculations to do in it. So let's go ahead and finish off 1.2. So the process that we were talking about in 1.2 was the idea of finding a limit algebraically. And this page in particular, we came up to the idea of the first thing you should always try is directly substitute in the number into your function. And if you get a real value, if you get an actual number out of this, then you found your limit. There's nothing else to do. So in number 14, we could directly substitute 3 in for all my x's, and we got out 4. Now I did show that this is kind of using some of those properties. You could split it all up to do this. There's really no point in doing that in a problem like this because it's pretty straightforward. In number 18 here, again, the first thing that we should try is directly substituting in the 3. So if I directly plug in 3, I'm going to get 3 squared minus 8 over 3 minus 2. Well, 3 squared is 9 minus 8 over 3 minus 2. 9 minus 8 is 1. 3 minus 2 is 1. So we get 1. That is your limit. So no matter what that function looks like, the limit as x approaches 3 is going to equal 1. All right, on the next page, things change a little bit. If I were to directly substitute 1 into number 22, I'm going to get 1 squared plus 5 times 1 minus 6 over 1 squared minus 1. So what we get here is the numerator is going to give me 1 plus 5 minus 6. 1 plus 5 is 6, minus 6 is 0. That in itself is fine. The problem is the denominator. The denominator gives me 1 minus 1, which is also 0. What I've actually written up there is a completely false statement. This doesn't work. You cannot divide by 0. That is a problem. The fact, however, that you ended up with 0 in both the numerator and the denominator is actually a good thing, because typically if you get a 0 over a 0, that indicates that there's going to be some kind of a hole in the graph. And we've dealt with that. If you kind of peek down to number 40, you can see right around where x is negative 1 on that graph that there's a hole in the graph. This usually means that a limit exists. So I am actually going to cross this out because this is actually not a true statement. It doesn't work. But that means there's got to be a way for me to find the limit. So this is where the algebra kicks in. This is where we have to do some factoring. And I don't know what your level of factoring is. I can't assume one way or the other. I'm hoping that we can do some factoring here. If I factor the numerator, the first components of these, if you undo the FOIL process, which is really the easiest way to factor the numerator, have to be x and x. It's the only way I'm going to multiply those two things and get the x squared right there. The last components in each one of these parentheses has to multiply to give me negative 6. But when I multiply those, it also has to, well, I'll go one step at a time. There's two possibilities for getting 6 out of your multiplication. It's 2 times 3, or it's 6 times 1. 2 and 3 in this case will actually not work, even though you might look at that and say, oh, wait a minute, I remember FOIL, outside and inside. 2 and 3 have to add up to 5, which is that middle number. They do, except for the fact that one of these, because this is a negative 6, has to be positive, one has to be negative. You can't take negative 3 and positive 2, or negative 2 and positive 3, add them and get 5. That just doesn't work. So I know that the numbers here have to be a 6 and a 1. And I know because that 5 is positive, that when I do my inside terms, the ones right here, that's going to give me positive 6, and the outside terms, I'm not going to put a little arrow there, but the x times the 1 would have to be the negative. So I get x plus 6 and times x minus 1. You can always double check that by foiling it back out, and you will get the numerator. The denominator is the difference of squares, and that's one of those special factoring things. You have to recognize x squared and 1 as both being perfect squares, and then if that's the case and you have a subtraction sign in the middle, they factor to be x plus 1, x minus 1. Okay, and that's going to be a common thing that we'll see. And the reason that this is good is because now the x minus 1s will cancel out. And that's really good because really it's the x minus 1 that's giving us a problem. When I plug 1 into x minus 1, that's what gives us those zeros. The zeros have now canceled out. Now I can go back to direct substitution. So I'm going to rewrite this with just what's left over. And now if I plug 1 into the numerator and the denominator, I would get 7 over 2. That is the limit of this function, which means that there's a hole at 1, but both sides as we approach 1, it's not showing it graphically, but both sides as you approach x equals 1 would approach the y value of 7/2. That's one algebraic method. So factoring is a possibility, especially if you have polynomials on top and the bottom, which is a rational function. The one in number 28 is not rational because there's a square root in it. That is not polynomial. It's not rational. So there's got to be another way to do it. Well, again, the first thing you always do is check. If I plug 9 in, the numerator gives me 9 minus 9, which of course is 0. The denominator gives you the square root of 9, which is 3, minus 3, which is also 0. Okay, I did not write it in this case. Ignore my little messages there. Sorry about that. I did not write that in this case just because I want to save some room. What we need to do in a case like this, anytime you have something where you've got a root like that in the top or the bottom, you have to multiply the top and the bottom both by the same thing, because that's multiplying by a factor of 1. What you have to multiply by is what is called the conjugate of the denominator. And if you haven't heard the word conjugate before, the conjugate is the same two terms but the opposite sign from what's there. So that's going to end up being a plus because the sign that's currently there is a minus. But I also have to multiply the numerator by the same thing. Okay, now you might be looking at these thinking, oh man, this is going to be a mess. And it can be a little bit of a pain, but it's not horrible. The easiest way to do this is to put these in parentheses, so that when we go ahead and FOIL these, because that's what you're going to have to do, you have to FOIL the numerators and FOIL the denominators, things are going to be a little bit easier. If I multiply, let's work with the denominator first. Oops, I forgot to rewrite the word limit, because I have not actually been able to plug in the x equals 9 effectively yet, so I need to rewrite the word limit. If I FOIL my denominator, square root of x times square root of x, well, that's the square root of x times itself, which is the same thing as the square root of x squared. Square root of x and square are inverse operations, so they're going to get rid of each other, which leaves me with x. Then I have to do the outside, which is the square root of x times 3. Well, that's going to be 3 times the square root of x. So that's going to give me 3 times the square root of x. If I do the inside pieces, that's going to be negative 3 times the square root of x, which is minus 3 times the square root of x. This is the good part about the conjugate. Those two things are going to subtract to 0. The middle two terms of the FOIL will always subtract to 0 if you multiply by a conjugate. So the middle two terms I can not even worry about, I can ignore. But then I still have to do the last times the last, which is negative 3 times positive 3, and that's going to be minus 9. And you might be looking at that saying, well, that's not going to help me because if I plug 9 in, I still get 0 in the denominator. Let's see what happens with the numerator first. So I'm actually not going to distribute out the numerator, and you probably don't want to do that. That's going to be 9 minus x times square root of x plus 3. And this is why. Hopefully, and this is a little tricky, hopefully you notice x minus 9 is exactly the opposite of 9 minus x. They are exactly the opposite things. The bottom has a positive x and a minus 9. The top has a positive 9 and a minus x. Exactly the opposite things. Well, if you think about it, and I'm going to put this up here on the top, anytime I divide two things which are exactly opposite of each other, I'm always going to get -1. If you divide any two numbers with exactly the opposite signs, every single time you're going to get -1. So when I divide this 9 minus x and this x minus 9, because they are exactly opposite of each other, it's going to give me -1. So I'm going to simplify before I try and plug that 9 back in. I'm going to simplify this by these things canceling out, but it does give me a -1. And it doesn't matter where you put that. I probably should not put it there, actually. Let's put it up here on the top. So now all I have left, because I have no fraction left over, is the square root of x plus 3 times -1. Now I can directly substitute the 9 in for x, and we should be okay. If I plug 9 in for x, I get the square root of 9, which is 3, plus 3 more, and then I have to multiply that by -1, so 3 plus 3 is 6, times -1 is -6. That's the limit of number 28. All right, the algebraic stuff is the most difficult. You're going to have to do some factoring. You're going to have to do multiplying by conjugates. Those are the most challenging ones to do. All right, down here. These are not nearly as hard. Determine whether the function is continuous over the interval from -6 to +6. So if I look at my graph, as x goes from -6 to +6 on the first one, on number 38, it is very clear, hopefully, that you can see that these are not continuous. And the reason for that is because there is a jump right there. It's completely separated. You'd have to pick your pencil up off the paper to keep drawing that graph. There is a separation, not continuous. In number 40, it is also not continuous because of that right there. Again, there's a hole in that graph. You'd have to pick your pencil up to keep drawing the graph. So that would not be continuous over the whole interval from -6 to 6 on the entire graph that you see there. Both of them are not continuous. And the reason for that is, in this one, the limit as x approaches 1 of my function does not exist. It has to be the same from both sides, and it's not. From the left, it's 2. From the right, it looks like it's -1. In the second one, the limit actually does seem to exist, but the function at -1 does not exist. And that's actually not an f in that case, it's k. And I've actually kind of answered one of the questions that we're getting to right after this. So now let's go down and do 45. And I guess I probably should have said 46. Nope, 45. It's all A through F. Okay. I have definitely answered one of the questions for you guys already, but we'll still go through it. We want to find the limit because all these refer to K, so it's the number 40 graph. Find the limit as x approaches -1. Well, as x approaches -1, from both sides of -1, it appears that these values are approaching the value 2. It's not there, but they are approaching 2. So this limit does have a limit of +2. Okay, find k of -1. We just determined that. I wrote that in the green up there. There is no value there at k -1, so this does not exist. DNE. There is no value. So part C says, is k continuous at -1? Why or why not? Well, the definition of continuity says that a function must exist at that value, and that function's value must equal the limit. Well, obviously neither one of those things are true because the function doesn't even exist there. So this would not be continuous, so not continuous. And the reason for that is because the function does not exist. at x equals -1. All right, and then our last one, find the limit as as x approaches 3, and as x approaches 3, so 3 is right there, so as x approaches 3 from both sides of 3, it looks like we're right here. We're approaching -2 from both sides. Does k of 3 exist? Well, k of 3, sure, that's an actual point. It's the point I just put on the graph. There's no hole there. It's an actual part of that red line, and that value is -2. So then is k continuous at x equals 3? Well, the limit equals -2, and the function's value at 3 equals -2. Those two things are equal to each other. Therefore, the function is continuous at x equals 3. And again, graphically, you can see that. It doesn't break at x equals 3. But the reason for that would have to be written as, yes, it is continuous at x equals 3. And the reason for that, because the limit as x approaches 3 of k of x equals, don't want to use f, I should use k of 3. Those are the same. Okay, and that is how you would actually state it. All right, I believe that finishes up 1.2. Nope, it doesn't. I'm sorry, there's one more page. Yep, here we go. This will finish it up. So let's go ahead and look at 56. So 56 is a piecewise function, which changes, it looks like, at x equals 4. We want to know if the function is continuous at x equals 4. Well, in order for a function to be continuous at a specific value, the limit must equal the function's value at that point. So I've got two sides of 4 I would have to check. I need to check the limit as x approaches 4 from the negative side of g of x. And I've got to check the limit as x approaches 4 from the positive side of g of x. Well, the limit from the negative side of g of x is going to be if I plug it in to this one. So if I plug 4 into that one, 1/2 of 4 is 2, and then add 1 to it, we get 3. If I want to find the limit from the right side of g of x, that's from this one, because that's when x is bigger than 4. So I would plug 4 into there and get -4 plus 5. That's 1. So the limits aren't even the same. There's actually another reason why this would not be continuous, and if you look really closely at your constraints, this one is x is less than 4, this one is x is greater than 4. Neither one of those things has an equal to symbol at 4, which tells me that there's actually not even a function's value at 4. So not only does the limit not exist because it's different from both sides, but the function doesn't even exist at 4. And you could use either one or both of those as explanations. So the limit as x approaches 4 of g of x does not exist, and g of 4 does not exist. Therefore, that's what those three little dots mean like that. G of x is not continuous at x equals 4. Okay, hopefully that makes sense. All right, is number 64, is that function continuous at x equals 3? Why or why not? Easiest way to determine this is if you plug 3 in and it gives you anything other than 0, then you're going to be okay. It's going to be continuous because the limit will be the same as the function's value. So I can just directly substitute 3 in, and we're going to see if this is the case. 1 over 3 squared minus 6 times 3 plus 8. So that's going to be 1 over 9 minus 18 plus 8. 9 minus 18 is -9, plus 8 more is -1. So I get 1 over -1, which is -1. The function does exist at x equals 3. The limit is also going to exist at x equals 3. So in this case, the function f of x is continuous at x equals 3. And it's because the function and the limit are going to be the same thing. All right, that's the end of section 1.2. I will come back with section 1.3.